In what example 6 is similar to what we have discussed just now. It's about a car going round the turn. Okay, so here the engineer would like to design a bend in a road which has a radius of curvature 30 cm. He estimates that the average mass of the vehicles using the bend will be 1000 kg, so that is the average mass of a vehicle. And the average speed was also given 50 km per hour. So he wants the vehicle to be able to negotiate the bend without having to rely much on friction between the tires on the vehicles as well as the road. So you can take the friction to be negligible here. And what he wants to do is to reduce the likelihood of skidding, even in wet weather. So how did he do it? He achieved it by banking. Okay, if you recall, we mentioned banking in the last lecture. Banking refers to the banking angle refers to the angle between the vertical axis of the earth and the vertical axis of the object. So if you look at the back view of the car, and if there is banking, you realize that the vertical axis of the car, right, will not be parallel to that of the earth. So by doing that, if you look at the free body diagram, the normal reaction force will have a component that is towards the center of the circle. Okay? So without friction, if there is banking, a car will still be able to go in a horizontal circle. Okay, so I'll give you some time to look at A. Again, I'd like to repeat the strategy here. Whenever you are asked to find any information and you're not too sure what to do, you always start with free body diagram. So you have the car. Forces acting on the car will be the normal reaction and the weight. So here you are asked to find what is the banking angle. What is the optimum banking angle that the bend should have, so that even a vehicle with worn out tires, so you can assume that the friction is 0, okay, can still make the turn safely. Okay, so step 1, we always draw free body diagram. Step 2 will be resolve forces. Consider equilibrium in the vertical direction. And horizontally, is there any equilibrium? No, because it's going round in a horizontal circle. Okay, so the approach is the same. So I give you some time, you work it out now. So you should be able to recall what you've done in forces and dynamics. Vertical equilibrium, mg will be equals to the vertical component of the normal reaction force. So you have mg equals to n cosine theta. What about horizontally? What force do you have? There's only one, right? So it's an unbalanced force, and this force must be equal to the centripetal force. Okay, so by resolving the forces, we actually introduce the angle theta. So the question here is asking for the banking angle, which is the angle theta. So what's the best way to solve for theta with equation 1 and 2? What will you do? Divide? Yes, divide. Okay, so you can take equation 2 divided by 1, and then you work for your theta. Okay, so if I take equation 2 divided by 1, which is same as the previous examples, right? The previous two examples, we end up with tangent theta again. And the equation is still v squared over rg. In some textbooks, they actually have this formula, this as an equation for you to recall. But I don't think you need to memorize it. Okay, because you can always do vertical equilibrium, then horizontal, there will be circular motion, equate to centripetal force. You get this equation easily. Then from there, I substitute in. Okay, the speed is not given in meter per second, so you need to convert, and therefore the answer is 3.2 degree. Very good. Okay, with that, let's take a look at part B. Not done. Okay, in part B, you introduce frictional force. Okay, and in the question, you are told that the frictional force is 6 times the normal reaction force. Okay, so you have an expression for the friction. The friction is dependent on the normal reaction. You're asked to find out the maximum speed which the car can still negotiate the bend without skidding. Okay, so in addition to the normal reaction force and the weight mg, I have to add in friction. Okay, because for a car going around in circular motion, it will have a tendency to skid out of the circle. So friction is opposing the motion, friction will be downwards. Then I also label in the angle. This is the banking angle that you obtain in part A. Okay, you're given that the friction is 6/10. Then you do the same thing again, vertical equilibrium. Okay, so vertically you should have 3 forces now. The weight, which is vertically down, as well as the friction. Okay, so you can either put them on the same side as mg, or you subtract from the normal reaction. Okay, so there will be a vertical component for the normal reaction. So you have n cosine 33.2. Okay, then the friction, the vertical component, sine 33.2. So you get one equation. Okay, but this equation does not give me the speed. So I need to introduce another equation. So what equation would that be? I've done vertical, so the next one will be horizontal. So it's the same thing. Okay, horizontally there will be 2 forces. If you resolve your normal reaction, there will be one component towards the center of the circle, another component from friction also towards the center of the circle. So these 2 components add together must be equals to the centripetal force. So these 2 components provides the centripetal force. Okay, then you will have to recall the formula for centripetal force and then solve these 2 equations for your V. I'll give you some time, you try to do it. Okay, the final answer is 24.7 meter per second. I would expect you to know how to solve 1 and 2, right? Okay, the physics part will be to come up with equation 1, vertical equilibrium, as well as for circular motion, you have the centrifugal force to be provided by the the horizontal component of the n in friction. Then after that, it's just about math, how you solve these two equations. The only unknown here in these two equations, the only unknowns are your n, normal reaction. Your friction can be replaced by 6 over 10n. Okay, so the friction is not a problem here because it's reduced to 6 over 10n. And so the only unknown will be your v and your normal reaction. Two equations, two unknown. Solve them, you should end up with the answer. Some of you say just use GC, can. Okay, you just key into GC the values, then you get a final answer, can. Okay, all we want to see, our marking point will be, you have equation 1, that is one concept. You have equation 2, that is second concept. Third one, correct answer. So 3 marks for this part. Okay. The process, how you solve it, it is not important. Okay, let's move on to the last book example that we have in this lecture. Okay, here we have something similar to the challenge one, right? Instead of balls in the pail, we have a bucket of water. Okay, you're told that a rod of length 1 meter is fixed to the handle of a bucket of water. The water is forced to execute uniform circular motion in a vertical circle. If the bucket is moving with high enough speed, it is observed that no water falls out of the bucket, even when it is inverted like this, okay, upside down. So explain why this is so. Do you believe that no water will fall out of the bucket? Just like the ball? Anybody want to try? Okay, but I didn't bring a bucket of water. I bought a bottle of water. Okay, what happens if I were to turn it upside down? Of course, must be in a vertical circle. If it's not in a circle, I turn it upside down, you can see that the water will all fall. So what happens if I were to swing it in a vertical circle? Any volunteer? Can you see the water? Can you see the water? Can you see? At first I used tap water, but students told me they cannot see. Okay, so I colored the water. So now I'm going to swing upside down, and then you see whether the water stay in contact at the bottom of the water. Anyone want to try? Are you worried that the water will spill out? Yes. That means you don't trust students. Yes. When it's upside down like this, there are two forces acting on the water, right? What are the two forces? The weight and the normal reaction force. If you swing it fast enough, the mv squared over r. What is mv squared over r? The centripetal force. If the centripetal force is bigger than your weight, then the rest balanced by the normal reaction, the water should stay there. Do you believe this? Yes. Anybody want to try? What happens if the velocity is not high enough? What will happen? Then the centripetal force required, the mv squared over r, if it is smaller than the weight, then the water will flow. Okay, so the concept here is to swing as fast as possible, such that the centripetal force is larger than the weight. Okay, so this explanation we have seen it previously. Why is it that it's not falling out? It is because the weight and the contact force, right, actually provides the centripetal force. So none of it is used to pull the water down. Okay, with that, let's move on to part B. Now we are going to do some calculation. You're asked to calculate what is the minimum speed of the bucket. Okay, in order for it to stay, in order for the water inside to stay. Okay, so for part B, at the top right we have the normal contact force, which I call it N, and then we have the weight, which is mg. So we know that in order for the water to stay, we need mg plus N to be equal to mv squared over r. Okay, but the question is asking for minimum speed. What will the minimum speed be? It will be when the centripetal force is equal to the weight, with the normal reaction equals to 0. That means it's just contact, just the right speed for it to stay there. Okay, anything smaller, it will drop. But if you go higher speed, larger than the weight, what happened? Then there will be a normal reaction force. That means your water is actually pushing against the base of the bucket. That means it will sure not fall. Okay? So in this case, if we want the minimum speed, it will be when N is just 0. When n is just 0, your centripetal force will be equal to the weight of the water. And when this happens, the V will be equal to root G, R. So as you can see here, it's actually independent of the mass. It's dependent on the radius and the gravity. Yeah, the mass cancel off. Okay, so from here we can see that the minimum speed, right? Okay, for you to do something successfully like what I did just now is 3.1 meter per second. Okay, then we move on to part C. Part C is when the bucket is not at the highest point but inclined at an angle theta to the vertical. Part C actually Part C actually asks you to find the point at which the tension in the rod is the smallest. Okay, so I'm going to draw a generous situation whereby the bucket is at an angle theta respect to the vertical, as shown in the diagram. Then, first step to do, draw free body diagram. Forces acting on the bucket of water will be the tension, as well as the weight of the bucket and the water. Okay, then we need to resolve forces. But here, we are not resolving it horizontally or vertically. We are resolving the forces along the rod. Okay, so that is the angle theta respect to the vertical. So I will have T, which is the tension, minus the component of mg. So you resolve along the rod, your mg will be mg cosine theta, and this must provide the centripetal force. Okay, centripetal force is always directed towards the center of the circle. So the direction that I'll be interested in will always be towards the center of the circle. Okay, so far we've been doing horizontal circle, vertical circle. That's why we resolve horizontally, vertically. But now, at this position, right, the centripetal force is not horizontal, not vertical, but at an angle theta to the vertical. Okay, so I will have to resolve the forces in that direction to find out what the centripetal force is. Okay, rearrange. My tension T will be mg cosine theta plus mv squared over r. So the question here asks the point at which the tension in the rod is the smallest. So what is the variable here? What will affect the tension T? Theta, that's right. So in order to get the minimum tension, I need the smallest value for cosine theta. So when is cosine theta the smallest? Okay. So that is the question that you need to ask. When will the tension in the rod be minimum? And where will this occur? So we know it has to do with cosine theta. Okay, the minimum value for cosine theta will be not 0, but minus 1. Right, that's the smallest value. Okay, so in order for cosine theta to be minus 1, that will be when the angle is pi or 180 degree. So this will occur when the bucket is at the highest point. Okay. So the tension will be the lowest, and the tension at the top will be given by the centripetal force minus mg. Similarly, I can ask you, where will the tension be the greatest? Again, you can use this same equation. It will be the greatest when cosine theta equals to 1. And where will that be? When theta is 0, that means it's at the lowest position. Okay, with that, I'm done with C. Now move on to D. Now this is in discussion to how T actually vary with your theta. You are asked to sketch a graph of tension versus the angular displacement theta of the bucket. So this is the equation. Okay, T is related to theta by this relationship. So your end result should be a cosine graph, okay, shifted up by mv squared over r. Okay, so this equation is from part C, like what we say, the end result, right, for the graph should be a cosine graph shifted up by mv squared over r, because you plus a constant mv squared over r. The maximum value will be when cosine theta equals to 1, and the minimum value will be when cosine theta equals to minus 1. Okay, so that will be how the graph will look like. Okay, just now we mentioned when the bucket is upside down, that is angle is 180 degree, the tension is the lowest. Okay, when cosine theta goes to 1, okay, that is when theta is 0 or 360, that will be when tension is the maximum. So the shape of the graph here should be a cosine graph. Okay, we are done with the work example in the lecture. Now we move on to tutorial. I'll start with tutorial question 1. After this lecture, right, the next topic will be on gravitation. After you have completed the lecture on gravitation, I'll be back to see you for math tutorial on motion in a circle. Okay, so we'll continue with the tutorial after gravitation. Okay, so now take out your tutorial. Question 1. Question 1 is quite similar to the lecture work example. Okay, question 1 talk about the Earth going around the Sun. Okay, in tutorial question 1, you're asked to find the mean speed. That is your v. Mean angular velocity, omega, of the Earth in its orbit around the Sun. Okay, in the work example I did is the Earth rotates about its own axis. So the period is 24 hours. If it's around the Sun, it will be 365 days. And then you need to convert that period time to seconds. So question 1 is a warm-up exercise. Okay, you just need to recall omega equals to 2 pi over t, and to find your omega. So the answer is 1.99 times 10 to the power minus 7 radian per second. The second part is recall the concept V equals to R omega. Okay, so you sub in the value for the radius of the orbit, which is given, and the answer above for omega. So that is your mean speed, 2.99 times 10 to the power 4. Okay, so like what I said, this is just a warm-up exercise, similar to the lecture work example. So now we move on to question 2. I'm going to give you some time to try out question 2. It was a past year A-level MCQ question. Okay, but here I didn't give you the choices. So you work out the answer. take a look at. Okay, let's take a look at how to solve this problem. Are you all ready? If you are ready, can you let me know you are ready by not talking? Okay, let's check answer. Okay, some of you finish this question very quickly. That's very good. Because MCQ, you should not take more than 2 minutes. So for this one here, you're asked to find the centripetal acceleration of the student at Singapore. Okay, another one is at Cambridge. You are given the radius of the Earth as well as the angular velocity of the Earth about the axis. Okay, so we know that the Earth rotates about its own axis. So we assume that it's vertical. Okay, so this is the vertical axis to simplify the problem. For the student at the equator, he will be going round in a circle like this, where the radius of the circle is the radius of Earth. Okay. What about for student at Cambridge? He will also be going round in the circle, but what can you say about the radius? It will be smaller. Okay, so you need to draw to see for yourself. Okay, so this will be the circular motion made by the student at Cambridge, and therefore the radius will be smaller. So I will need to go and find that radius. That's why the angle here is required. Okay, so with that understanding, I need to recall the concept. I want to find centripetal acceleration. I'm given radius, I'm given omega. So of course the concept to recall will be A equals to R omega squared. Okay, then Singapore, the radius of the circle of the student will be the same as the radius of the Earth. And for the student at Cambridge, the radius, what you need to resolve. Okay, so you should end up with the radius of the Earth cosine 52. Actually, for the acceleration at Cambridge, you can just take the acceleration at Singapore, then cosine 52 also. So one of the good strategy, right, when you do a physics problem will be to draw diagram to help you to visualize. So in this case, if you were to draw the circular path taken by the student at Cambridge and at Singapore, you'll be able to see that the radius is different. And then from there, it is likely that you're able to solve it correctly. Okay, with that I'm done with 2. Question 3 is very similar to 2. Okay, similar idea. But instead of equator and Cambridge, question 3 is looking at equator and North Pole. What can you say about a man standing at the North Pole? What is the radius of the circle? Then from there, how do you answer the question? I move on. Okay? Let's take a look at diagram 1. They say the weight of the object mg is measured by a spring balance at the North Pole, and at the equator, right, there is a small difference between the weight measured. If you look at diagram 1, you can see that there are two forces acting on the object. What are the two forces? The weight, due to the pull of the gravity, can you see there is a downward force, mg, and then the upward force, which is the pulling force, okay, on the scale balance. So at the North Pole, because the man is not going round in the circular motion, because he's standing at where the axis is, so he will be just turning around like this, okay, and not in the circle like this. So this is the axis, so he will be just doing like this. So the radius is 0. Is there any centripetal force if there is no radius? There isn't any centripetal force. So for this, right, the mg will be equals to Fn. So the two readings are equal. Okay, so this is what we just discussed. Highlighted the force here. This is the weight, and then this is the reading on the scale. These two forces are equal. So if you were to stand on the weighing scale at the pole, okay, what you see on the weighing scale will be your actual weight. What about at the equator? Okay, this is diagram 2 at the equator. At the equator, there will be circular motion. Okay, and the radius of the circle will be same as the radius of the Earth. So again, if I were to look at the free body diagram on the object, I will have the weight, mg. Okay, by the way, mg is not down. Mg is always towards the center of the Earth. So that's why you see in the diagram there, okay, it's towards the center of the Earth. So that is my mg. And then the reading on the scale, I call it Fs. Are these two forces equal? No, very good. Why not equal? Because the object is going round in a circle. So there must be a resultant force towards center of the circle. And this resultant force is provided by mg minus Fs. Okay, there are two forces acting on the object, namely the weight mg and the reading on the scale, which is Fs. So these two cannot be equal in magnitude. Your mg must be larger. mg minus Fs must be equals to centripetal force. So what will be the reading on the scale? If I make Fs the subject, you see that the reading on the scale will be mg minus the centripetal force. So for all of us here, we are at the equator. When we stand on the scale, actually we weigh like it's not our true weight. Okay, because why? There is part of the weight that is used to provide the centripetal force. So at this moment, if you were to go over to say Cambridge or North Pole, you find that there is an increase in the reading. Not because you gain mass, but because over there the centripetal force, let's say at Cambridge, is smaller, or at the pole there's no centripetal force at all. Okay, so the reading reflected will be closer to your actual weight. So at the equator, we all actually weigh lighter. Okay, so that is the idea behind it. I have actually sent you the solution, the qualitative solution. Okay, so you go and refer. Okay, so I don't think I want you to copy here. I have already sent you this solution. You can refer to your email. Okay, so over here, what we are talking is at the North Pole, right? The mass is on the axis of the rotation, and therefore the Earth's circular motion have no effect. There is no centripetal force required. So the two readings will be equal. Okay, let's move on to question 4. Another MCQ question. I give you 2 minutes, you try, then you tell me what is your answer. Okay, how do you start off with this question? What do you do? Free body diagram. That's right. Okay, like what I always mention, if you do not know how to solve this problem, don't just give up. Start by drawing free body diagram. Okay, so you consider the free body diagram for object Q. There will be two forces, namely the tension and the weight mg. Okay, so resolving it vertically, you'll find that the upward component of the tension will be equals to mg. So you end up with T cosine theta equals to mg. Okay, then we know that the tension in the string, right, is T. That means this is also T. P is in equilibrium, right? So tension T must be equals to 2 mg. Okay, so from here you get T equals to 2 mg by looking at P. The tension, upward tension, must be equals to the weight 2 mg. So you sub that in. So from here you can work out the angle theta. So once you have the angle theta, okay, horizontally you know that the horizontal tension, component of the tension, will provide you the centripetal force. Okay, so if you don't have time to copy, never mind. Okay, I already sent you the solution. You just try to understand what I'm trying to say here. The strategy is always the same. Consider vertical forces. Then it happened that when I do that, I managed to get theta. Then you do it horizontally. The horizontal component of tension provides the centripetal force. So R is the only unknown. From here you solve R. So you get 0.31. Okay, so you go back and try. We stop here. So I will see you again after your gravitation lecture.